Evening. I know it's cold and it was some flights here that might be snowing as well. I appreciate everyone taking the time out to come and attend this session. Today we'll have a double bill. We'll have two talks. The first one is by Armand Vidande, who's a manager of technology and digital integration at Resonant. And thanks Deloitte for sponsoring this event as well as Curelet for allowing us this fabulous facility and hosting our meetup over here. So Armand is going to be talking about where did text embedding come from. I would like him to come and start the talk. Thank you. Thank you.
All right. Yeah, this is for you, yeah, not for me. So, thank you so much for showing up. We were expecting more, but it seems like the weather was really working fine for everyone. So I usually start my my slides with this sentence. For whatever reason, I've been doing this for the past, I don't know, 6-7 years now, and it kind of is stuck with me. Ralph Emerson is somebody that I really like. I encourage you guys to go and take a look at his work. He's not a data scientist, by the way. It's just someone from literature that I really like, but some of his sentences are really cool. So knowledge exists to be imparted. So let's try and see if we can do that today. What I'm going to talk about today is, it might actually be very low level to some of you, and my apologies in advance. This is going to be the start of a series that I was hoping to do. So it is basically taking care of the infrastructure, so to speak. So hopefully in a couple of months I'll be back with more interesting stuff and using everything that I'm going to talk about today about. And that work is going to be done by using the help of a few of my friends who are here as well. So today's topic is, as Zia mentioned, where did text embeddings come from? Again, first in the series. And as I mentioned, the next talk is going to be with the help of my friends who are sitting here as well. This is a picture of my colleagues. You could see them right at the end of the aisle. So there is a reason that I'm going to talk about this, because we thought it's better if we do something geeky for today as well. So in the picture you can see Vikram, from left, Vikram, Lucas, myself, and Dawar. But why am I talking about this? Because we thought that it's cool if we do something geeky. So by show of hands, who knows who that picture is, who that picture belongs to, who's the person in the picture? I kind of tricked you guys. The URL was mentioning the name, so I changed it into Bitly so that you don't cheat. But so the way that these guys are sitting over there, we thought that maybe we define a distance function, which is right there. And then we realized that it's actually very cool if we start experimenting with these kinds of things. So what we have is, the distance function is log of a function f with base e, and then the function f is basically between words I and j. And that's a uniform average of another function between wi and wj and wi and wj prime. And this g function is basically the sum of the absolute value of another function, which is taking every character in wi and wj and wj prime. And then we realize that we have to, so we define h as the ASCII code, basically, for each one of these characters, and then we realize we have to do some padding. So it's some sort of a crazy story that happened, over the course of, I guess, 2 weeks. So we started with something really simple, and then we realized that even that simple problem of the distance which people are going to sit from me is going to take more work than we were expecting. So that's the cool thing about it. And then the result was, and the answer to the first question I asked from you guys, the person in the picture, both here. So that's Jeff Hinton when he was a kid. And then the result is the distance between Lucas and Dawar and Vikram represented over there, hence the way they're sitting. So that's the geeky stuff. which I thought might be fun, and then another picture of Jeff. I think that's 2 years ago. So with that kind of crazy introduction, let's dive into the topic of today. So it's a fairly simple agenda for today. We're going to talk about why embeddings exist. So this kind of connects to another meetup that we had, I think, 2.5 months ago that you were talking about. Or no, somebody from Kite, Mandy, I think, was talking about. So it kind of connects to that if you were part of that meetup. And then we're going to take a look under the hood of some of these, so to speak, embeddings, to see if we can find something interesting. And with that, let's take a look at the why. Let's see what the problem is. So we have objects here and there in everyday life. And objects are, as we know, instances of different classes. And then we need a way to basically represent these objects in a way that is machine readable, so to speak. So we have different words for it. We have encoding, mapping, vectorization, embedding, blah, blah, blah. So all of these different names. And then of course, objects are also at different levels of granularity. So for the case of text that we're talking about today, we can have characters, words, sentences, paragraphs, sections, books, series, everything. So when we're looking at a solution to a problem such as finding a way to represent these types of objects, it would be really, really helpful if these representations are generic enough so that we could use that solution at different levels of granularity. And then connecting that to today's meetup, I took the first sentence in Mary's basically introduction, looking forward to our next session of the Waterloo Data Science and Data Engineering meetup. So we're going to look at how we could use the sentence in finding the problems with some of these old embeddings or vectorizations. So some of the traditional models that you've heard about, bag of words or bag of engrams, if you want to make it a little bit more general, and then one-hot encodings, count vectorizing stuff, TF-IDF, all of these names that you've heard about. Why they didn't work to the extent that people decided to work on more sophisticated embeddings. So back to this guy. Looking forward to our next session, blah, blah, blah. Then people started doing bag of words. They separated the stuff words, and then they realized that there are some context words that they're going to use. But, so I have to move this thing. Okay. So, but then they didn't really realize that, okay, so there are two words data here, and then the result that they're looking at only has one of those. So that's one. Then they started looking at, one-hot encoding at the word level. So you have a corpus of all the words that you have in your dictionary, and then you have your ones and zeros, things that pretty much everybody here, I think, has heard about. So you have a one where the word exists, and zero where the word doesn't exist. And again, they realized that there are some problems that we're going to talk about. And then they kind of moved it from word level to sentence level. So let's assume that you have that representation, very simple for this sentence. And then you have science and engineering, which are basically underlined over there because I wanted that to be, bolded for today's chat. And then if you want to have another, another representation for a very similar sentence, something like that, by switching engineering and science, you probably end up with something very similar, but not exactly the same vector. So as you know, as you can see, I simplified the vector, but still, the content is really, really similar, but the vectors could be different. And then what happens if you add a not before the data engineering? What's going to happen? Most probably another vector. So then the question would be, what's the similarity or what's the distance, if you're talking about the one with the not, between these vectors? The old methods, the traditional methods, are not capable of really, working the work that is needed. They can't support the bigger problems that people were trying to solve. They were just, the first step towards the problem solution. And then, so to wrap it up, the shortcomings, cardinality is an issue. The more words you have, the more your problems are going to be. And then nowadays, every day people coin another term. And then if you're talking about multiple terms at the same time, talking about the same content, then you have more problems because sometimes you have two words jamming into one another, talking about something totally different, such as big data. Big data has nothing to do with big and data, to be honest. And then, so that connects to the problem of non-generalizability. And so it's not generalizable enough for most of the tasks that people were trying to work on. And then the biggest problem of all, loss of context. These solutions are not, basically they're uninformed mapping. They're getting rid of some of the context that are in the sentences or in the paragraphs and so on. So for example, if you have a not at the beginning, so not looking, and then you have a not right before data engineering, these two backward same, totally different sentences. So people kind of started working on the new definition of embedding that we're going to talk about, even though embedding could be the same, like vectorization and things like that, but embedding in the sense that it's a neural embedding. So the bigger problem here was that they were interested in finding basically a mapping of a discrete categorical variable to a vector space, and they wanted this to be continuous. So some of the characteristics that basically helped people use this more was that you have low dimensional space. So for example, in the text domain, you jump down from 50K to sometimes 100, sometimes 300. And then another characteristic is that the space is continuous. It's not only 0 and 1 or 0, 1 and 2 when it comes to cap vectorizations and stuff like that.
I have a question.
Sure.
What do you mean by low dimensional? You refer at the size of the vector or the size of the sentence?
So it could be both, but in this case I'm talking about the size of the vector. So in the sense that what we had here, 3, or what we had here, relative to the number of words in your corpus, when you're using neural embeddings, the dimensions are much, much lower than that. So you don't need 50,000 words, so a vector of 50,000 dimensions. You could work with 100 or 300 or sometimes even less than that if you're working on your own text to train your embeddings.
So neural embedding, you refer that you are using neural networks?
Yes. So that's the generic way of defining embeddings these days, and that is part of the types of embeddings that I'm going to talk about later on today. So most of these solutions or most of these embedding types that I'm going to talk about are using some sort of a neural network to train an embedding space, and specifically for text. Yes. And then another characteristic here would be that they preserve meaning or context. So let's see how they do that. That's not as obvious as the first two, but then we're going to talk about the way that they're trying to solve that problem. Some applications, as you might have seen or heard, in finding similar objects to represent objects in a supervised learning task. So in our case, let's say sentences, or words, or documents, and then of course to visualize the object space. So neural embeddings are very helpful in that, in solving those types of problems or in those types of applications. With that, let's take a look at the what. So what are we talking about? What do we mean by neural embeddings? Because we're talking about a neural network, we usually have some sort of an embedding layer. So this is our projection layer. So we're going to talk about this layer in a couple of minutes. But as the question just happened to be, and here is the answer, it is a neural approach. So you're using some sort of a neural network to train these embeddings and get the outcome of the embedding layer or the projection of your input space. It is, and in brackets, usually, not always, a supervised learning problem that they're trying to solve, and then embeddings are a result of, or basically a side result. Sometimes it is, there are embeddings that are unsupervised, but we're going to talk about that later maybe. But mainly, these neural embeddings started to show value when people were trying to solve a supervised problem. And then your network is usually, it could be as simple as an input layer, an embedding or a projection layer, and then an output layer. If it's not as simple as that, then you basically have a bunch of projection layers in the middle. So this is something that we also know as a hidden layer. So you could have 1, 2, 50, doesn't matter. They're all part of the projection layer. So this projection layer is actually the important component within this solution, so to speak, to the embedding problem, and that is where these weights of the network are getting extracted so that people could use them to represent the objects that we started the conversation with. So these objects, again, words, characters, documents, whatever it is, at whatever level of granularity, people define some sort of a supervised learning problem again, and then the outcome on the side is going to be the weights of the embedding layer or layers, and then that is how people basically represent or encode their objects. So this usually has very deep connections with transfer learning. So what do I mean by transfer learning? In traditional machine learning, we usually have a task or some sort of a domain. We train and evaluate and test on, within that domain or on that task, and then we have a model, and then we use that model, we deploy it, we put it in production, and there we go. And then from domain to domain, usually these models are not transferred. But when we're talking about transfer learning, it basically means that you have a problem, you try to find a solution for it, and then as a side product of solving that problem, you end up having some sort of a knowledge, you gain some sort of an insight, and then you try to use that in solving a different problem that is very similar to the first one. Well, not very similar, but related, so to speak. So that's why when we go back to this problem, it kind of connects now. Neural word embeddings or document embeddings, or generally speaking text embeddings, are a byproduct of another problem that people are trying to solve, a supervised learning problem, as I mentioned. And then once that problem is solved, then people take a look at the weights of their projection layer or their hidden layers and say, interesting. So whatever I have trained my model with is now giving me some sort of an encoding space. And I could use that encoding space to encode or to project my input space. So that is what the relationship between this whole embedding or neural embeddings and transfer learning is from my perspective. There are cases where we don't really do transfer learning, and so that's not part of the conversation today, but hopefully in future, I could get a chance to talk about that in a different meetup. And as you probably, question? Yes?
Yeah, so here the new model, you obtain the new model from the previous model, like directly from, or you first go up to the stage of the first stage of model.
So you're talking about the red model?
Yeah, so if
not necessarily.
Not necessarily.
Not necessarily. You could use word embedding to solve a totally different problem. So that problem could, let's say, be sentiment analysis, right? The model for the sentiment analysis problem has nothing to do with what you have trained your, so for example, Word2Vec, right? But you're using Word2Vec embeddings, as an example, for your sentiment analysis model, as you know, from input to your first hidden layer. So models A and B do not necessarily have a lot in common, but they are related, so to speak, in the sense that the input sometimes is coming from a different task. It can, but not necessarily. Usually it's not. It's usually the result of model 1 is actually a lookup table, and that's it. So you take a look at, let's say, your word, and then you get a vector, and you just push that vector into your model B, for example, neural network or k-means or whatever you're trying to do with it. Right?
It's like the output.
Yeah.
So how do you know that you are right? Is that
Which one? The first one?
How do you know that the model, the green model, is fit to be used in the red model?
That's a very good question, and I personally do believe that even though people are using most of the word embedding, so I'm going to talk about the model called Elmo at the end of this talk, and part of the reason that people talked about, worked on Elmo was, and also another one from Facebook called FastX, was because the embeddings that you were training basically on a specific type of a task or a specific data set wasn't fit for the task that they were trying to use it for. So you can't really necessarily know. There's no generally agreed upon framework to make that decision, but there are some heuristics that people use. And as far as I know, and if anybody has a better answer to this question, for now everything is heuristic based, with a point that if your data space is pretty similar, so for example, if you're trying to solve a problem in social media, your embeddings shouldn't be trained on Wikipedia or Google News. Facebook might give you a better, but it's still considered heuristic. It's nothing concrete about it. And then the tasks. So if you're trying to do something that has to do with pictures and generating, let's say, a caption for a picture, right? Automatically generated using a neural network, then that task is different than just text summarization for a book. So you have to have your embeddings in a way, framed in a way that is fit for the task that you're trying to basically accomplish. But then again, that to me sounds more like a heuristic than a framework that
You can still measure the outcome and performance of your other neural model as well. Right? So it's not like you're not taking a blind trace. You're not just pumping data in. Whatever you're pumping in as features, you can still measure them, its effectiveness on the outside.
Yeah, so it's evaluation, the way that we do it, but it's not hard evidence because sometimes numbers might lie as well. Okay. So back to the poster boy, Wurtzweg. How many people haven't heard about Wurtzweg? Haven't even heard the name? Okay. Cool. So most of the people know about Wurtzweg. So this is basically one of the examples that a lot of people have heard about. And it's very, 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 very famous, and it's a good example of transfer learning. Because in this very simple picture, and in very simple neural network, which is, in brackets, not deep, just 3 layers, people are trying to guess context words, basically the words that are related to a specific word. So they get one word and they want to see the next words. So that's the supervised learning task, because they see some corpus of text, they see the sentences, they know which word is coming right after another one. So for example, in this case, you're looking at specific words such as ants, and you have you train your neural network in a way that it could give you probabilities for the words that are going to come right after the word ants. And by doing that, you have a neural network that is going to give you predictions. So whenever you say ants, it will give you 0.02% this word, and a lot of zeros and 2% another word, and maybe 10% another word. Probability, of course. But then, as a byproduct of this very simple network, people realize that the weights in the hidden layer could be incorporated to represent the words such as ant, because then you don't necessarily need 10,000 dimensions to represent all 10,000 of your words. You only need 300 neurons in the hidden layer to do that same, relatively simple job for you. So that is the ties to transfer learning, in a sense that you are trying to solve a supervised learning problem, but on the side you get something that you could use somewhere else, which is a 300 basically long vector that is representing each and every word that you're seeing in your corpus. So moving forward from the poster boy, let's see what are the other examples. So there are some famous embeddings that people use nowadays. I will try and go through a few of them today. Let's see how much time I have. What time did we start, by the way? Okay, cool. So some of these examples that you could see in this table, and this table is kind of an update from the link that you can see down there. I got rid of a few of the examples because I knew that there's no time to talk about them, and I added a couple that I really liked. So by the way, these slides I will put in the meetup link so that you could go and take a look at all of these links, especially the bit.ly at the beginning. It's an interview of Jeff Hinton with FastAI, I think. It's kind of very interesting. But then, as you can see, so in this table, very simple. There are some famous embeddings at the word level and at the sentence level. Of course, some of them you could use in both basically dimensions, but there are some strong baselines such as word select, log, fasttext, and then for sentence level bag of words, which people are still using for something as crazy as just doing not only let's say applying it to naive Bayes, but also still sentiment analysis. People are using bag of words and it's working, so it's a strong baseline. But then there are some state-of-the-art works that we are trying to touch with still, such as elbow and such as impercent. Doctor-like, I still consider it as a state-of-the-art because people are still working on making it a bit better. And then universal sentence encoder from Google. So these are just some of the examples. There are at least 20 others that we have heard about, and my colleagues and I will try to basically implement them or try to use them in different tasks to see if they're good for the problem that we were trying to solve. Back to the question that you asked a couple minutes before. Then let's take a look at the how. I'm going to start with a very old paper in the Neurons embedding domain. It's a paper from a couple folks from the University of Montreal. It's very famous in the sense that people tend to think at it as one of the one of the reasons that word embeddings took off, even though they're not as famous as word select and everything else. They kind of laid it down there for word select specifically. So this is the work from Bendu and I think 3 of his colleagues. And in this work, basically what they tried to do is this, a very classical type of a neural network that you can see in this picture, just 2 layers again, very similar to word select as you can see. And then the task they were trying to solve was, if I give you n words, can you give me the word that is coming right after it? So a window of, let's say, 5 words, what's the word at the 6th place? So it's kind of, again, a classic neural network, and it consists of just one hidden layer. It's trying to predict the next word, but let's take a look at the basically objective function here. Very simple in the sense that it only has a regularization term on the right, and then the function itself is 1 over t, which is the cardinality of your corpus space, and then you have a function f, which is getting the first n words, and then it's trying to guess the word at the location right after n words. So this is very simple in a neural network type of a setting. But then from here, people kind of started realizing that, interesting, so everything that is happening here, between these 2 layers, has some sort of a meaning. Because as I change my words, my first n words, I'm getting different types of vectors that are sitting in my hidden layer. So are there vectors that are, similar for similar words? They started experimenting with it. And then a few years, was needed for people to experiment enough so that they realized that something like this could happen. So this is another piece of work that is kind of connected to the idea of word embeddings. This is, a lot of people know this as the CMW model. So I'm not going to focus on the architecture of the network here, but what they realized from working on this problem was that if they train this model for a specific task, and I'm not going to focus on the task for now, word embeddings could be trained on the side if the training is happening on a sufficiently large corpus of words. And they talked about, their data set was mainly documents. And then these word embeddings carry basically syntactic and semantic meaning, and then they could improve the performance of some sort of a downstream task. They continued working on this from 2008 to 2011. They published another paper, and this is basically the gist of what they have done. So why is this important and how different it is from the first one is the reason I decided to put this here. As you can see, the objective function is relatively different from what we saw in the first one. So the solution here to basically avoid the heavy computation of what Benjo and the colleagues were trying to do was to not use the expensive softmax function, but to use another type of objective function. So the function f that you can see here is actually a scoring function. And then what they were trying to do was that if you have a window of, let's say, 5 words, 7 words, if I change the word in the middle in a sentence and give a wrong word, I need to have some sort of a scoring function or a scoring mechanism that would give higher probabilities to the correct word and lower probabilities to the wrong word. So if I give you 5 words, you would know with the probabilities that the model is going to give you whether or not the word in the center is actually correct or not. So if the probability is very low, relatively low, then you would know that the scoring function is, trained so that that probability be low, so that you know that the word in the center is actually wrong. That word doesn't belong to the collection of 5 words. So I think that's a very genius way to solve that problem, because back then they didn't really have that much computation power in 2008 and 9. And then, so I'm trying to go back and forth between my notes and these slides, and sometimes it doesn't work.
You mentioned this is called C&W?
C and W, so Colbert and Weston, for the 2 people who are working mainly on this project. But a lot of people in the word embeddings or neural embedding domain know this as a CW approach, this scoring mechanism, so to speak. And then obviously you can see that they're trying to minimize this objective function by taking the maximum of 0 and 1 minus the difference between those 2. And then X here is actually the window size, and W is the actual word that you're trying to predict. So that's the, again, supervised learning in the sense that supervision comes in the format of a window of 5 words or 7 words. So, moving forward, from these guys then came in 2013 suddenly the work from the folks from Google, which resulted in Word2Vec. People just went nuts suddenly overnight. You see multiple examples of this type of a picture where is an advocate for why Word2Vec works really great, and a lot of people fell in love with it. But then the gist of this picture is that word embeddings can capture context, and then they can capture relationships between different objects within your domain. So that if you know the vector for Paris, and then you know the vector for France, and you know the vector for England, you kind of can compute the vector for London. Or, there are relationships between the vectors of mother and boy and daughter. So that you could use those types of computations if you have, word embeddings or sentence embeddings or whatever you're embedding at whatever level they are. So word embeddings, Word2Vec usually comes in 2 different variations. So let's take a look at different variations of Word2Vec and see what type of supervised learning problem are these a byproduct of. So the first one, as people might know about it, is called continuous bag of words. And it's fairly simple. Given a context of a word, such as a window of 2 words before and 2 words after a word, can you give me the probability of a specific word? Very similar to the C&W problem that we were talking about a couple minutes ago. So here, this is basically the objective function that they were trying to solve. Again, the objective here, so the problem is very similar to the CMW. The objective is very, very, very similar to what the first paper in 2003 was trying to solve, which is, if I know n words before and n words after a word, can I train a neural network that could give me the probability of a specific word, so that if I give my whole corpus of words, I would know that a specific word or two words have the highest probability, and everything else is potentially garbage. Okay, so here, what people at Deloitte tried to do, the team behind Word2Vec, was instead of feeding n previous words into the model would just receive a window before and after. So that's the main difference from what people were trying to do before, by guessing the word right after a sequence. And talking about another variation of the way that people were trying to train embeddings, the other variation is called skip-grab, which is kind of the reverse problem. So if you have a word, can you give me the context, the words that come around that word? So if I know I'm talking about ants, am I talking about running? Am I talking about smell? Or am I talking about basketball? So by training a neural network that could do that, this was the objective function. As you can see, very, very similar to what we were seeing before. 1 over t, which is the cardinality of the corpus. And then they were trying to basically take a look at the log function of the probabilities of all of those words based on all the sentences that they could see in their corpus. So even though it is very similar to the work that people were doing before, skip-gram, the objective was copying basically some work from a couple of years ago, but both skip-gram and continuous bag of words suddenly took off because the hyperparameters of these networks were basically selected in a way that could contain meaning. So a lot of people still use 300 as a dimension of their hidden layer because Google decided to do that. And it's a very famous example of when people are talking about training word embedding on their own corpus. A lot of people start from 300 just because Google decided to do that. Even though it's not, it's not a very good way to solve that problem. You should go through all of the experiments. But, it took off because of those hyperparameters, because those embeddings could actually capture meaning, because the relationship between cities and countries existed in the word embeddings of 300 dimensions in their hidden layer. And then again, it's just a very shallow neural network. It's not a deep neural network. So, moving forward, 2013, we see GLOVE. So GLOVE is actually, it stands for global vectors. So there's a difference. And the main difference is in the name. It's so obvious. So here you're not looking at 5 words before and 5 words after. You're taking a look at the whole universe of your corpus, whether it is characters or documents or words. So it is in a sense global. So it captures the meaning of one word embedding with the structure of the whole observed corpus, not only the few words before and after. So that's the major difference. GLOVE vectors are trained on global co-occurrence counts of words, and it's basically the way that they try to solve it is, calculating the co-occurrence matrix and running a very simple SVD, and then they realized that interesting, one of these matrices on the side is actually containing things that are very similar to word embeddings that we've seen before. So let's try and do some experimentation over there. What they decided, what they found out, which was very interesting to me, was that instead of using the actual co-occurrence counts, they decided to use the ratio of these, sorry, not counts, probabilities. They decided to use the ratio of these probabilities. And then they realized that, this ratio actually contains some information that is encoding the differences between different types of words. So here, if you take a look at it, it's fairly simple again. So you have some sort of a scoring mechanism, and then you have your different words. You have two biases that are talking about, the way that your network is going to be trained. I can't really remember what the last term is all about, so sorry about that. But here's the ratio part that I was talking about. So instead of actually using the probabilities within the co-occurrence matrix, they realized that their scoring function should be based on, the values inside the co-occurrence matrix, the probabilities of co-occurrence, over the maximum of those probabilities to a power of alpha. So they decided, I think by the end of the day, they decided that 3 over 4 is the best value for alpha. And again, interestingly enough, or maybe funny enough, a lot of people who are trying to solve, the problem of word embedding nowadays using the glove mechanism, using spacey and things like that, they just set alpha to 3/4 for whatever reason, even though it doesn't connect to their problem.
How you determine the probability?
The probability of co-occurrence?
Yeah.
So whenever you see two words next to one another in the whole corpus, those two words are co-occurring.
That means you have to compute it a priori, yeah?
Yes. They actually do that. And that's another, that's one of the reasons that training glove takes a lot of time. And then right after that, you have to do, singular value decomposition, which also takes a lot of time. So that's why people, I think, glove was IBM, right? Or I can't remember. But not everybody could do it. Stanford, yeah. So not everybody could try. I mean, we tried, and we couldn't do it on our cloud instances because it was taking so much time. Even we can't use it when we're trying to just load the embeddings. We're having problems these days.
Out of curiosity, how you implement this?
How do you implement this?
Yeah, how you store these probabilities? Just out of curiosity.
So I haven't personally tried to basically train a network on a data set other than the data set that comes with the glove algorithm in the corpus that they, in the repository that they put on GitHub. And that data set is actually fairly simple. But if you want to train it on something like Wikipedia or Google News or Google Books or Amazon or something like that, it's going to take a lot of time. The one that I have tested myself, it's just fairly simple. I just did, a matrix count, and then created these ratios, and then from there you just, have your very simple neural network that I tried with 3 layers and 4 layers once. Both of them pretty much the same accuracy level, so to speak, even though the embeddings were different. But then by the end of the day, the mechanism is already there. I think Spacey also has implemented glove. So a lot of people just, use very simple APIs to just call the glove object and then pass in some parameters, again, alpha 3/4, and then we hand in their corpus of documents, tokenize it, and then the outcome is going to be a bunch of word embeddings.
But this is open source, yeah, the implementation. If I want to go and look it up how it's done in the guts, I can see, yeah?
Yep,
Okay.
yeah. So one thing that I personally tried with glove that was very interesting was what happens if you do not use that X max, which is the highest probability, but you just, go with something else. So I tried with, I think my highest probability, so the data set that I was using was publications, the AAAI publications of 2013 and 2014, which you can find on UCI. I was wondering if I can train something, word embeddings for those guys. And then I said, okay, I think the highest co-occurrence probability for me was 5% or something like that. And then I decided to change that to 50%. And then it just broke the whole thing. Embeddings were terrible. So there was a reason why they decided to go with X max over there. But it's just experimentation. Based on my experience, It was just experimentation. So even the guys at Google, the guys at IBM, whenever it comes to tuning the algorithm or tuning the hyperparameters, they just go with all the different variations that they think might work, and then, and of course there's a reason behind it, some sort of a heuristic where it makes sense, and then they just pick the winner. But I have seen word-to-vec embeddings that were trained on 100 dimensions, and they also work. So it really depends on your corpus size as well. But yeah, the code for throughout exists, and you could experiment with that as well. So moving forward, FastX from Facebook, 2016 and 2017, people once again, they kind of, over the course of a night, they realized that, wow, something crazy is happening here. And the major idea behind this was, or the major difference here was that they were using basically something very similar to skipgram and something that I didn't mention for word-to-vec, which is called negative sampling, plus word morphology. So what they're trying to do is they were basically taking into account the internal structure of words by splitting a word into tokens of different sizes. So basically these tokens are bags of characters, or engrams of characters. I think they tried something between 3 and 6 characters, and then they added something like a starting token and ending token to the word as well. And then by the end of the day, this is how word morphology looks like to the folks in this example in Facebook. So they start from the actual word, from the 2 tokens that I mentioned, start and end, and then they start counting. For example, 3 characters. So starting token W and H, and then WHE, and then they go all the way, and they kind of combine all of these when they're trying to represent the word where. So in that sense, the word her is different than the word morphology subset, or the character engram of HER within where, because it doesn't have, the word her has the opening and closing tokens, but HER here doesn't have. So in that sense, if you have different words with HER in the middle, that specific piece is going to represent a piece of meaning over there. But when you're looking at the word her with opening and closing tokens, then that's a different type of meaning. So doing that, a word is represented by some of all of these vector representations of its engram plus itself. So that's basically the gist of the innovation behind FastX that kind of made similar embeddings, but based on a different type of what should I say, assumption, so to speak. That they would say, okay, so I don't really only care about the word where, I also care about all of these characters that is building up the word where. And then I think, again, if I'm not wrong, what they decided to do was that they added everything that has 3, 4, 5, and 6 characters, and nothing more. So if a word has more, I think they just define their window between 3 and 6 for these character engrams. So that's just the idea behind FastX. I mentioned it. Cool. And then what they realized the outcome of this was that this type of generating your word embeddings by summing up all of these representations of each one of these morphological, basically, engram, is actually able to better represent or model infrequent words. So this is one of the problems that word-to-vec had, and they tried really hard to solve it. But then if there's a word, whenever it's in 2003, they need you all the way to CW, to word-to-vec, to whatever else. If you have a word that is not part of your corpus, or you don't really see a lot of that in your corpus, you always have a problem with that type of embedding. It's not as accurate. But using this way of basically representing a word by its components, so to speak, linguistics components, the folks at Facebook realized that they could better model the infrequent word in their corpus. And then the embedding that a lot of people are talking about nowadays, ELMO, which stands for Embeddings from Language Models. So ELMO is basically also in a sense similar to what FastX did in the sense that, it also uses a character-based model to solve the, the problem, but it's trying to solve another type of a problem as well, which is the problem of polyphony. So for example, to define that problem to you guys, we've all heard of the example of going to the bank to, deposit some money, or we decide to go and sit at the bank of the living. Same word, different means. So ELMO is actually started as an attempt to solve that type of a problem. Can we have word embeddings that can cure that disease, so to speak? ELMO embeddings are able to handle representations of words that do not appear in the training corpus as well. So in a sense, it's a little bit better, very similar to FastX, but a little bit better in terms of representing non-existing words as well. And then the way that it works is that it is derived from a bidirectional long short-term memory network, so LSTM, bidirectional LSTM, and then this is trained on a very large corpus of text. So what they initially tried with was the 1 million word benchmark data set. Another interesting thing about ELMO embeddings is that each token, so I'm going to talk about the tokens in a minute, but each token is assigned a representation that is a function of the entire input field. So again, the idea is very similar because we talked about it a couple of minutes ago. The fact that GLOB is taking, a global look at your corpus, not, specifically at the context or a local view of your word. But ELMO also does that, but for token level, not word level. So here is the objective function for this specific model. So I'm not going to focus on this again a lot, but I just wanted to mention that those two terms that you can see there are basically representatives of your bidirectional LSTM. So it's the forward and the backward, basically, case of your network. And here the data here is basically representing your LSTM here, and then these are the tokens that you're going to see in a minute. And then what they were trying to do is basically training a neural network that would minimize this, loss function. So how does it work? So I'm going to take a couple minutes just to talk about ELMO because everyone's clearly about ELMO. So it's very simple. So you have a word down here, and then I mentioned about bidirectional LSTM. But before that, what they do is that they try to create some sort of a character embedding first. Then they hand those characters into a convolutional layer with some max coding. And then they hand this to another thing that is called a highway network. So a highway network I'm going to talk about in the next picture. But it's mainly a way for people to make sure that the flow of information from one layer to another layer makes sense. Now let's take a look at, and then that is the input to your bidirectional LSTM. So that is how bidirectional LSTM is represented here. So even before going to train your model, your neural network, the folks who were behind the works at ELMO did a lot of changes, made a lot of changes to the words, and that's why they're doing everything at the character level or token level, so to speak. So what are the steps at ELMO, and then we will take a look at the steps in the picture as well. First thing first, what they were trying to do is they were trying to convert, as I mentioned, each token to an appropriate representation using character embeddings. Why is this important? Because we could pick up morphological relationships and features that word-level embeddings are going to miss for sure. Another reason is that it could ensure that we could find some sort of a valid representation for word-level embeddings for words that are out of your vocabulary. So if you have not seeing something in your vocabulary, in your corpus. If you're looking at token level, then you can kind of make sure, and again, this is, so to speak, a heuristic from linguistics that people knew about before, but nobody was using it in the neural embedding domain. So they realized that using this would ensure a valid representation for out of corpus words as well. Step 2, they put this into a convolutional neural network, a convolutional layer, as I mentioned, and then this is to basically a way to pick up features, n-gram features, very similar to what people do with machine vision to find, let's say, vertical lines and horizontal lines and eyebrows and stuff like that for pictures, but here, in the sense that we could capture features of n-grams that are representing words. So that's the reason why a convolutional layer is, exists on there. And then this helped them build more powerful representations for both the feature level, n-gram level, and the word levels. And then they passed this to a 2-layer highway network. So a highway network is, again, as I mentioned, it makes sure that the information, the flow between 2 layers, first of all, is correct, and it is smooth. So after they did that, now let's take a look at opening this into this type of the architecture of the network. So the sentence they were looking at, part of it is moment the absurdity is recognized. So the first thing first, they take this, they put this into character embeddings, then it goes to some sort of a convolutional layer so that different characters that come right after one another could create features for different words. So if you have, again, 2 words with the token HER in them, this is a shared token, very similar to when you have, let's say, the curve of a car in 2 different pictures, you would know that this is a curve of a car. Or if you see an eyebrow in 2 pictures, you would see that this feature is actually the feature of eyebrow of a person. And then the max pooling right after that, and then the highway network in the sense that you can see here. So they take this into a layer, and then they take the same input layer and put it up there, and then sum them. And then this is when the bidirectional LSTM network actually starts. So this whole thing is basically pre-processing for training your model. And then after they do that, then they end up in this kind of a network, a 2-layer bidirectional LSTM network. The very interesting thing that they have done here, and so there's not enough time for me to talk about residual layers today, I think. But one thing that they have done here is that for the actual sentence, the representations that they get from the highway network, they connect the input layer to the output of the next layer using a residual connection. And then this goes all the way to training the model or the network for guessing the next word, so that V would go all the way to cat would go all the way to is, and so on and so forth. So they would read the sentence from the start to the end to the start, and bidirectional. And then they would realize that we have 3 vectors here. The X, which is the pre-processed version at the character feature level, or token feature level, better to say, which is the X for the word happy. And then the weights for the output of the first hidden layer, and then the weights for the output of the second hidden layer for that specific word. And then what they do is, I think here as well, they either add all of these, or just take an average, a uniform average, all 3 of these vectors, and then that would be the embedding for the word happy. So there's a lot of work that has been happening to basically to create an Elmo embedding. But then it is very, very powerful in the sense that it could probably pretty much solve all the problems of the embeddings that existed before Elmo. So we kind of learned all the lessons from everybody from 2003 all the way to 2017, and then we captured everything. They put it in there. They got ideas from machine vision. They got ideas from linguistics. They kind of bumped everything into one huge algorithm, and then by the end of the day, they realized that, yeah, interesting. So if we have these three layers, these three vectors, let's just, add them up, and then we will end up with some sort of an embedding. So in that sense, there's a very crazy pre-processing step. It takes a lot of time. I tried it, it didn't work. My computer crashed. Well, not my computer, my TPU instance crashed, so I don't know how to solve it. But then, using that again, I think the guys, if you talk to them afterwards in the break or after the second talk, they can tell you, even using the elbow and the glove embeddings, we're having problems with them. So I don't know how they trained it, but these are basically the ideas behind it. So moving forward, there are a lot of other very recent embeddings, not only for text, but also, first of all, for different levels of granularity of text. So you could have it for document level, for paragraph level, for sentence level, but also for different types of objects. So we have category to vector, sense to vector, speech to vector, impercent, which is sentence level from Facebook, URL fit, skip thought, also skip thought, and then all the way. So there are all these examples that, I encourage you guys to go and take a look at them and see how crazy they are. The one very interesting example that I plan on playing around with is BERT, which they announced a couple of weeks ago from Google that they've open sourced it. I also believe that order embeddings is something that's going to take off. I think Bish is not here, so Bish is the person who has actually introduced this to me, and I have a plan of playing with this paper, and so if I find something interesting, maybe later on I'll come and report that to you guys as well. But there are all these links that you could go and take a look at the papers and see if you can find something interesting to share with us in the future. And with that, I kind of wrap it up. This is another picture that I usually put at the end of my slides, which I really like, and I think that so far a lot of people like as well. It's about Python giving you the ability to fly. And with that, I wrap it up. I know I really talked a lot and very fast, but if there's any question, I'll be happy to answer. If not, I'll just hand it to Zia and Mary.
So I was wondering, what is the source of innovation here? So we have all these methods here that I understand the people who publish them that have experimented with them. Mm-hmm. So what we can do is to see if it is working for our language domain, or you can improve those algorithms. Or
so just to make sure that I understand the question, innovation from my side or innovation from the side of the papers and the embeddings? Which one?
Both.
Okay. From my side, no innovations yet. We are trying though. What we are really trying to do is apply all of these different ways to solve a very specific problem, which I'm not allowed to share with you right now until we pass the demo phase, which is happening in a couple of weeks. So hopefully by the end of February, maybe February-ish, all four of us can come back and share a little bit of insight about the way that we try to solve that problem. What I can tell you is that the problem is in the realm of natural language generation. So we're trying to basically generate from a combination of linguistics, heuristics, and deep learning methods to automatically create paragraphs for a specific task. So that's the gist of the problem we're trying to solve. But these are tools in our inventory. So that's one. The innovation from the perspective of all of these folks, I personally do believe that, especially nowadays, innovation is not necessarily creating something new. Innovation for me, and Elmo and Glove are two very fantastic, three very good examples of it, is understanding why something works in a different domain, ties to transfer learning from the question before, and not just using it. If you know, for example, why features are being captured from a convolutional layer in machine vision, then you could take that lesson and apply it to a different domain. So that's the definition for innovation for me. If I can just take something very, very, very small from some other domain and try to abstract that idea and think of how I can apply that abstract idea in another domain. I think I could then, be more than confident enough to call myself an innovator. But then I encourage, a lot of people that I can see here to also answer that question about innovation. Maybe after. I think there's another question, but innovation to me is not just creating the next penicillin or coming up with another concept for an airplane. It is trying to find a very simple problem with a very simple solution that works for everyone.
So we have time for one more question.
Okay.
I had a couple, but later. So I am
We'll chat
struggling
later.
with the same thing right now. That first I have to train hyperparameters for a particular model, for example, fast text, and I don't know what to do. And there is no handbook that says when this happened, you probably want to increase that.
Yep.
But even within fast text, it has two models. It has continuous background words and skipgram. A more general question is, how do I decide which model works better for a task? But particular to fast text, why would anyone use skipgram over CBEL or vice versa?
Well, skipgram versus continuous bag of words, to me, first of all, we kind of had this conversation about how you decide, right?
Yeah.
To me, it's all about heuristics. And the connection to the way that these algorithms work. If what you are trying to do, and that's the way that I tend to do it, if what you're trying to do is find a word, using these embeddings, find a word in a context, right? Then don't try and do something that is trying to find a context, that was trained on finding the context of a word. I would never do that. It might work and it might be wrong, but I think that the tasks that you are trying to basically, the problem that you're trying to solve should have some sort of a logical flow of relationship between one another. So that you can't say, okay, so I trained this on, so I'm saying something else, I was saying something else before, and I'm basically trying to say something else right now. So if you're training something on continuous bag of words and trying to do sentiment analysis, it might work. But if you're trying to do something, you were trained something on continuous bag of words, and now you're trying to use it in this, skipgram model, I personally believe that it's not going to work because they are contradictory to one another. And then for fast text example, also the corpus on which your embeddings were trained also is important. Again, if you're trying to solve the problem of the Quora dataset or Stack Overflow dataset or Twitter dataset, Facebook dataset might be good. But if you're trying to, in my problem that I was trying to do, if you're trying to write, have your machine learning model write something for you that is official, then using Facebook text dependent embeddings, I think is not, it might work, but it's not generic enough in the sense of a task. It might be in the sense of a data set. So those are the two heuristics that I have found that are working relatively okay, but I don't have an answer to that question, to be honest. If you ever find a way, please share it with me, because I don't believe anybody knows an answer to that question.
PhD thesis topic.
Yes, maybe even 5 PhD topics.
Some PhD. That's the research perspective to start.
5 minutes break.
5 minutes. Okay.